at MNIT Jaipur. So he has completed his PhD from DTU New Delhi, and he has published more than 50 articles in international journals and conferences, and peer-reviewed international journal and conferences. So his main research interest lies in computer vision, image processing, big data, machine learning, and deep learning. So with this introduction, now I'd like to invite Dr. Ashish Kumar Tripathi to kindly start the session.
Okay, very good evening to all of you. I think I'm audible.
Yes, sir, you are audible.
Okay. So I'm just sharing my screen. Okay, yes, sir. My screen is visible now?
Yes, 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 yes. You can continue, sir. Over to you.
Okay, good evening to all of you. Welcome again to this FDP on modern computer vision. So in this session, we will learn about the generative adversarial networks and what are the basically how basically this generative adversarial network works. Uh, what are the applications where we can use this generative adversarial network model in our research based problems, and how to basically implement it. So we will also do hands-on on this particular session. So just before starting this session, might be possible you already have some acquaintance with this term that is called generative adversarial network. No doubt that's quite a popular word nowadays with the evolution of generative AI. So before starting the session, let's have a question that I have these four images A, B, C, and D. So which one of these image is real? You can just okay. And moreover, meanwhile, during the session, if any question is coming to your mind, you don't need to wait till end of the session. You can just write your question or your query in the comment box. I will keep on answering, and just make this session interactive rather than just keep on listening and listening. So it will be my pleasure if you will be asking questions meanwhile during the session. So that will make this session more interactive. A, B, C, and D. So what do you think? Which one is the real one and which one is the generated image? Anyone, if you have any guess, you can just write your answer in the comment box, and we'll start from this point. And not only the comment box, you can just also unmute yourself. You can just also ask your query. I will be happy to answer in between. I think if someone is writing here. So okay, let's answer. So if you see these images, all these images are basically the fake images, we can say. None of the image A, B, and C and D is the real one. So this is the power of generative networks. Nowadays, we are able to generate the images which are very, very realistic. And not only the images, this is one of the application. Nowadays we can just generate images, we can generate video footages, we can generate some text which will be very, very close to the real one. And majority of the time it is very difficult to distinguish between which one is the real or which one is the fake image. Particular adversarial based models, rather we can also do a lot of things using the generative adversarial networks. Because this FDP is on the vision part, so I will be focusing more on the computer vision based applications, that is image and video processing kind of this. So for example, I have this source image, and if I want to just change the gender of image using this particular facial expressions using features which are derived from this source image, we can just do it. We can just change the gender of this particular image using the generative adversarial network, using the generative artificial intelligence. And for example, if this is the image we want to just add some beard, or we just want to change the hairstyle, we can also do it using the generative adversarial based models. That is the changed version of this particular image. We can also do some kind of pose change, that is called also called as style transfer. So we can also do style transfer kind of things. We have just changed the pose of this particular image. This is the lightening. If I want to reduce the age, we can also do it like this. And one of the popular application might be possible, you have seen in the social media sites, like how will you look after 10 years or 20 years or 30 years. That can also be perfectly done by the generative adversarial based models that are called GANs. So here in this case, in case number 2, we can see that this is some image. We have just increased the age, we have just changed the gender, we have, after changing the gender, we have just added some glasses. So these are the applications that we really can do using this particular generative adversarial models. And not only this, many more are coming with the evolution of research over the course of time. If we see some other popular applications or actions of generative adversarial networks, then we can see that we can also do some kind of image resolution based tasks. So for example, this is the image, and we want to just change the color of the image. We can do it using the generative adversarial network. If you want to just remove the haze from background, we can also do it using the generative adversarial network. So for example, this is one of the very popular application of generative adversarial network. So that if you have some research based application, but those images are of low resolution, we can just increase the resolution of the image or quality of the image using the generative adversarial based network models. Not only this, for example, you are acquiring some real time data in some extreme weather based conditions. For example, you are acquiring data in the month of December, and you are able to see that there is a lot of fog or smog in the environment. So the images which are coming are blurred and not good one. So we can also do some kind of image dehazing with this generative AI based concepts. So these are some very popular real world based problems that we can do using generative adversarial network. Not only this, for example, if you have like a data imbalance problem. Data imbalance problem means that you have two classes, class 1 and class 2. In class 1 you have 2000 images, and in class 2 you have only 1000 images. So might it be possible the trained model may be more biased toward this particular majority class, that is class C1. So what we can do, we can just perform some upsampling. We can generate 1000 more images using the GAN, and we can just upsample this class C2 to make it 2000. So we can just and that is quite obvious problem, uh, especially in case of medical imaging kind of things, where we have less number of data samples from the diseased class generally as compared to healthy one. Not only this, if we want some image captions, if you want to describe some image, then we can also do using the generative adversarial models. For example, so this is the input image that we have given uh, to some particular GAN based model. So this is the two types of GAN which are describing this particular image, that a cow is standing in the field next to the house, a cow is standing in the field with the house, a cow is standing in a field of grass. So there are some of the image descriptions that the AI based models are basically giving, and this is the basically human based image captioning, that gray cow walking in a large green field in front of house. So what we can do using the GAN, we can also do some kind of image descriptions. In this particular image number 2, we can see that a train that is pulling into a station, a train that is going into a train station. This is basically described by the generative adversarial network model. So we can just check and see that what is the power of generative networks nowadays. So based on this, plenty of thoughts may come in a mind after this session, that what are the possible applications and how we can leverage the strength of these generative adversarial networks in our research-based uh, problems. Now, coming to the point that before going much more into details and before discussing even more about the applications of generative adversarial networks, let us see how what is GAN and how basically it works. What is the core idea behind generating the text or image or video footages using the generative adversarial based model? So, what is the meaning of GAN? GAN means generative adversarial and networks. So, G for generative. What is the meaning of generative? Generative means that we are going to generate some data, generate some data. And exactly, if I talk in technical terms, not the data, rather we are going to generate some probability distribution. Probability distribution. And if you have mimicked some probability distribution which is close to the real one, then it's quite easy for you to use that probability distribution model, to use that probability distribution and generate some images which are close to the real one. What do you mean by A means adversarial. And if I talk about adversarial, what is the meaning of adversarial? Adversarial means competing or conflicting kind of things. So why this is adversarial? Because in this we are going to use two networks, G and N, where G is called as generator, and G and D, where G is called as generator, D is called as discriminator. So these two networks, G and D, will try to compete with each other, will try to fight with each other in order to have better training, better training. So generally what happens, we used to compete with our colleagues, we used to compete our classmates, and if that particular competition is healthy one, then might be possible we both have some kind of improvement over the course of time. So this is the same case with the G and D. G and D networks works with the different intentions, and they will keep on competing with each other, and that's why uh, they will be keep on training, keep on learning, and ultimately we will be able to have a probability distribution model which will which is close to the real one kind of thing. And what is N? N is basically networks. So these G and D, if I talk about G and D, both are the networks. So it is not mandatory that which kind of network we will have. You may use any deep network model. So initially it was started with basic MLP, that is multiple perceptron model, and after that we kept on enhancing, and as per the requirement we started using some transformer based models as well. So that may be any deep neural network, or that may be a simple multi-layer perceptron model. So that will depend upon the kind of requirements. So I have described all these three terms, that is G, A, and N. G for generative means we have to make a probability distributed model. We have to make a generative model which will be able to generate some data. A for adversarial, that means the training of both the networks is going to be done in adversarial manner, in a conflicting manner, in a competitive manner. And N for network, that means we are going to use some deep neural network based models in order to accomplish this particular task. Now the whole idea of this generative adversarial network, that is G and that is GAN, will keep on revolving uh, behind around two words, that is called as G and D. G is for the generator and D is for the discriminator. These are nothing but some neural network models. These are nothing but some neural network models. That's it. And it may be anything that I have already discussed. That it may be MLP, it may be some deep neural network, some CNN based model, some transformer based model, or something else. As per the requirement, different kind of requirements have different kind of generators as well as different kind of discriminators. And this particular model, that is called GAN, it was introduced in 2014 by Ian Goodfellow. And from that point, after the introduction of this particular uh, generative adversarial network in 2014, this has become a buzzword, and a lot of researchers started developing a number of modified GAN based models and a number of variants of GANs. A number of variants of GAN has been developed over the course of time. For example, CGAN, Style GAN, SR GANs, and the list is very large. Depending upon the requirement of the user, researchers kept on just developing the models um, according to their requirement. And not only this, just after the introduction of this word, you can say that evolution of generative AI has started. And after that, uh, a lot of generative AI based bots have been also developed and introduced in the literature, like um, OpenAI, Chat GTP, that is, and Gemini, and all kind of things. So you can say that this is the basically backbone of the generative AI that has been introduced by Ian Goodfellow in 2014. Now coming to the point, what is G and what is D? So what is the role of G generator? The role of generator is to just create the fake data, just to create the fake data, and this fake data should be very close to the real one. And what is the role of the discriminator? The role of the discriminator is just the opposite of the generator. The role of the generator is basically to just classify between the real and the fake data. That means it has to just distinguish between the real and the fake data. So why the things are adversarial? Because if the generator is poor, if the generator is poor, then the task of discriminator is easy. Why the task of discriminator is easy? Because if the generator is poor, then it will be able to generate poor quality images. Poor quality images. Poor quality images means the images will not be the images will not be close to the real one. Close to the real one. So if the generator is poor, that means it will not be able to generate the images which are close to the real one. And the images, if the images are not close to the real one, then the task of discriminator will become quite easy. That means discriminator can easily discriminate between the real and the fake images if the generator has not developed quality images. And vice versa, if discriminator is quite poor, that means if discriminator is not able to differentiate between the real and fake images, then the task of generator will become easy. Why? Generator will think that I am generating the images which are very much close to the real one. Why it is so? Because the discriminator is not able to uh, discriminate or classify between the image that I have generated and between the real image. So this is the reason it is called as adversarial, because the goal of both the generator and the discriminators are different. However, I will tell you in the upcoming slides that in order to be overall model be good, both should compete in a healthy environment. Generator should attempt to fool the discriminator, well as discriminator should try to discriminate between the real and fake images as good as possible. So I will just tell you the things in more detail in the upcoming slides, that how to do this and how we are going to perform such kind of training. Okay, so there are two classes that I have discussed generative in the case of GAN. So what are the two classes? One is the discriminative model and another is the generative model. So discriminative model is basically classification kind of task, and generative model is a basically generative model. We have to just develop some probability distribution model, generative probability distribution model kind of things, and the training has to be performed in adversarial manner. So what is generative model? The task of generative model is is to be trained on training data X. So from where this generative model will get training? From the training data X, that is the original data. That is the original data. Or you can say that is the real data. So generator has to be trained from the real data, that you can say it is sampled from the true distribution, capital D. So capital D is basically the probability distribution of the real data. Probability distribution of the real data. Distribution of the real data. And we will also have some other standard random distribution that is called as Z. So what is capital Z? Capital Z is basically random distribution. Random distribution, not the real one. I have taken some random probability distribution. And what is capital D? Capital D is the probability distribution of the true data or the real data. So these are the two terms that you have to basically remember, that D is the probability distribution of the real data, Z is any random probability distribution, and the task of the generative model. What is the task of the generative model? Task of the generative model is to basically convert this random data distribution to some other data distribution that is called as D dash, such that this D dash is very close to D. What is capital D? This is the real data distribution. This is the real data distribution. And what is D dash? D dash is the data distribution of GAN, or you can say generator. And what is the task of the generator? Generator have to take as an input the random distribution of the random probability distribution, and convert this random probability distribution to D dash, which is very close to the real one, so that in future it can generate the images which are close to the real one, No doubt I will keep on just explaining these terms again and again to make it very much clear till the end of the session. Now let's see mathematically in a little bit more detail, that how basically what is the meaning of data distribution, and how basically generator and discriminator will be trained, and how we will be able to achieve the objectives. So let us assume that what I have told you, that what is the role of the generator? The role of the generator is to take the input some random data distribution that is called as capital D. Some random data distribution. Random data distribution. You can assume that this is some kind of Gaussian data distribution. So what is this small z? Small z is basically uh, some sample of the randomly distribution that is called as capital Z. So small z is one of the sample of this entire set that is called as capital G. So this is basically random data distribution. So you can here you can just assume this shape as the probability distribution kind of thing. And what is this capital D? Capital D is basically this is original data distribution. Original data distribution. What is this? This is original data distribution. And from where this came? From the original data set. From the original data set. And what are these dots here? So these are the basically these dots are called small x. So these belongs to capital X. That means these small x are the samples of the real data. Samples of the real data. These are the small x. And what is the role of G? And what I have told you, G is nothing but it is some network. It is some neural network. Might be possible at this moment of time, assuming it that G is simple MLP, multi-layer perceptron model. What is the role of G? G has to take this random probability distribution, and if this is the trained network, if this is the trained model, this trained model is going to convert, is going to transform this random probability distribution that is called capital Z to D dash. That means this random probability distribution will be converted to D dash by generator network this. So this G network is basically take input as noise, you can say, and it is going to just develop some probability distribution model. And can anyone tell me that what is the objective of this probability distribution model? How this converted D dash, that means generated probability distribution model, will look like? How should it look like? Anyone? This should be very, very close to capital D. That means the generated probability distribution, that is D dash, this should be close to this. So D should be very, very close to D dash. So whatever the probability distribution model that has been generated by the generative network that is called G, this should be very, very close to the real one. This is the intention. So this is the basically motivation of the network that is called as G. So again I am going to tell, in entire GAN we have two networks, one is called as Z and one is called as D. So here what I am telling you, I am just telling you that what is the objective of generator that's called G. The objective is that it has to take some random noise belonging from 0 to 1, because it is probability distribution, and in case of the probability distribution, minimum value is 0 and maximum value is 1. So it is going to take some normal or Gaussian probability distribution and convert this probability distribution to D dash, and this D dash should be more or less very, very close to that one. This is the reason intentionally I have drawn this random distribution like in this oval, in this shape, whereas this is some kind of circular shape which is very, very close to the D, that is the original data distribution. Got the point? So coming ahead, if I talk about the overall architecture of the GAN, that is overall flow of the GAN, so this is the intention of generative network that I have discussed. And coming to the discriminator network, that is called D. How D work? D is basically network which performs classification task. Classification task. So basically we can see that G is a generative model, whereas D is a basically classifier. And what classification it has to perform? It has to take the input from the two sources. One is from the real data. This is the one source, and another is the data that has been generated by the GAN. So it is nothing but Z of Z. Got it? So it is going to take data samples from the two sources. And what it has to do, it has to basically classify that which one is coming from this source, that is a real one, and which one is coming from the generator, that is the fake one. And based on that, two losses will be calculated for the discriminator. So for example, uh, generator discriminator has just classified that this sample is the fake one. That means its classification is wrong. So we have to calculate the loss. And on the basis of loss, we'll keep on updating our network. Got it? So basically, we can see that in the case of GAN, this discriminator D act as a binary classifier. Uh, the task of the classification is to classify between the real and the fake kind of images. So this is the overall, basically the functionality or the task of the discriminator, that it has to take the data from two sources, one from the real, one from the generator, and it has to just tell, it has to just classify that which data is coming from the real data source and which data is coming from the generator. It has to accurately classify. And if it is not able to classify correctly, that means it has to retrain itself. It has to perform further training in order to do better classification in the future. So meanwhile, if you have any kind of queries or question, you can just ask me. You can just put in the comment box, or you can just unmute and ask. Overall, if I want to just summarize the things that I have discussed so far, we have a generator. Its task is to generate the fake sample, and it tries to fool the discriminator. And again, we have a discriminator. It tries to distinguish between the real and the fake samples, and it has to then, both the generator and discriminator has to train against each other, and we have to repeat till we get better generator and discriminator. So we need to improve both over the course of iteration. We need to improve G as well as we need to improve D, because for better GAN, both the generator and discriminator have better training and better understanding. If any one of them is weak, then ultimately our overall GAN model will not be that much efficient to basically classify between the real and the fake one kind of things. Again, coming to the overall GAN architecture, so far we have discussed in detail about the G and D, that is generator and the discriminator. Now coming to the overall architecture of the GAN, so we have the real world images, and these are some. This small x is one of the sample, so you can say that small x basically belongs from capital X. Capital X is basically set of all the real world samples, and small x is basically one of the sample that I have taken from capital X from the real world. This is the random noise, and the generator G has converted this noise in Z of Z using some network. And this is one of the sample that I have taken from the pool of the, this is the pool of the generated images. This is the pool of the generated images. So I have taken one sample from the real image, and I have taken one sample from the generated image, and the task of the uh, basically discriminator is to discriminate between the real and the fake one. So what is the real? So what is this dx? So dx is basically the probability value that has been obtained by the last R output layer of the last R output layer of the discriminator. So this is the probability value that I have got by the last layer of the discriminator, and for the real images, this value should be close to 1. And what is d of z? This is the basically probability distribution that has been generated by the generator, and after applying discriminator model here on this data that has been generated by the generator, it should give a value between 0 and 1. And ideally, the value, what should be the value of this one? Can anyone tell me? It should be equal to 0. So ultimately what I have got from this figure, that d of x should be equal to 1, because this x is coming from the real samples, and this d of z should be equal to 0 if discriminator is doing its job efficiently. Then it should produce 1 for this, and it should produce 0 for this, because this one is coming from this fake sample, and this one is coming from the real sample. So again, capital Z is the random noise. It may be Gaussian or uniform, and this is basically uh, the input for the generator, which it takes, and over the course of time it basically keep on changing this distribution and make the distribution that is called as d dash, which is close to d, that is the original data set. Now let us also discuss that how this basically noise is converted to basically image. So for example, I have just used some function in the Python, and I have just created a noise vector. So this is a noise vector. Got it? And basically I have reshaped this noise vector in some other format, for example 8 cross 8 cross 128. Then what I may do, we may just apply this convolution 2D transpose layer to just again upsample it to 16 cross 16 cross 258. Again, as per the requirement, I have applied again a convolution 2D transport layer to just upsample it again, and again I have upsampled it. Then if I want a RGB image, then I can just again apply this to reshape in 64 cross 64 cross 3. So this will be a equivalent RGB image, and this generator is able to just create a fake sample that is cross 64 cross 64 cross 3, that is an RGB image. So we started with the random noise vector, and after just applying these layers, we are able to just reshape it and make this an image of like this, that is called 64 cross 64 cross 3, kind of this. Now in this session we will be basically doing some hands-on on the data that is called as MNIST data set. So what is this MNIST data set? MNIST data set is basically, this is a fashion data set. This is a fashion data set, and this data set consists of a lot of basically the samples, some kind of shirts, pants, coat, t-shirts, and all kind of things. And how basically this GAN model is going to work on this particular data set. So for example, this is the same thing that I have already discussed, but this time I am discussing it with some uh, real world example, so that we can just visualize even in more better way. So for example, this is the MNIST data set. So these are the data, the capital X, and what is the small x? Small x is one of the sample. So we can say that if I have chosen this one, so this is the small x. So this is the one of the sample that I have taken from this capital X, that is large data set. So for example, this is one of the sample that I have taken, and this is my discriminator network. So what is this? This is discriminator network. Discriminator network. And what I have already told you that both the G and D are nothing but they are some neural networks. So I have taken two data samples, one from the real source and one from the generated image. So this is the fake image that I have generated, that or that has been generated by this G. And how this G is working? This G is taking some random noise. It is taking some random noise that is called as capital Z, and it is converting this random, this neural network that is called G. This neural network is converting this random noise, because this is a generative network. So this is converting this random noise to this some sample that is called fake one. And what is the task of the discriminator? It has to just discriminate. It has to basically produce one for this, and it should produce 0 for this. Means that the probability value of the output layer for this sample should be 1, and the probability value for the generated image, this should be equal to 0. If discriminator is able to do so, that means discriminator is doing its job correctly. Otherwise, discriminator needs further training. If discriminator is producing 0 for this or 1 for this, that means discriminator is not able to classify. It need to be retrained to become more stronger, to give more challenge to the generator like this. Got the point? So I hope you are getting the things, and no doubt if you have any doubts in your mind, you can just ask me before going ahead, because this is the core concept, and we must be clear till this point. Okay, coming to next, how basically uh, training of the generator and the discriminator is being formed. So this is the same thing, that for example, this generator has generated this image, and we can say that this may be in the initial phase. This may be in the initial phase. Why it is so? Because generator is basically taking input from the random noise that is called as capital Z. So generator has started from the pure noise. That's why it is generating images which is a little bit noisy one. So if I talk about the discriminator can easily say that this is the fake one and this one is the real one. Why it is so? Because this is quite noisy kind of image. And here one very important point that has to be noted, that why we don't do the training of generator and discriminator at the same time. While discriminator is trained, G is kept constant. And similarly, if G is trained at the time of training of generator, discriminator is kept constant. Why it is so? Because if you are keep on uh, basically training both, so what may happen that we don't want a uh, discriminator that can that can never get failed. Why it is so? Because that then it will be very difficult for the generator to improve itself over the course of time. So we do the training of generator and discriminator in step by step fashion. We just train the generator, then discriminator will discriminate between the real and the fake one. And when discriminator start discriminating between the this and this, then we will again train generator. Generator will improve itself, and after that what we will do, generator will become more robust. So again it will give a challenge to discriminator, this now check me, and again the discriminator will definitely uh, keep on just checking and classifying that which one is the real and which one is the fake one. So the important point that is that while the training, if I am training discriminator, I will keep generator constant, and while training the generator, I will keep discriminator constant. Got it? So if I'm training generator here, then generator will generate images. It will give to discriminator, and discriminator will just say 0 or 1. Again, this generator will uh, give another image to this discriminator. Discriminator will tell 0 or 1. Got it? So, and we will keep on looping. We'll keep on looping unless and until we are not able to fail the discriminator. So that means if for fake discriminator is saying 0 and for real discriminator is saying 1, that means the task of generator is not over. We have to train it further. Train it further. Got it? And as soon as this saying that for fake it will say 1 and for real it will say 0, then what we'll do, we'll just stop this process of training the generator, and we'll move on discriminator. That means we are able to fool this particular generator model. Now coming ahead, if I talk about training the discriminator, it is going to take the real world samples. It is going to classify real or fake, and based on that it is going to calculate the loss, and it has to reiterate again. It will classify the real and fake, calculate the loss, and back propagate itself. So it will keep on training, and here you can see that in image we have logged the generator. We are not generating, we are not training the generator at the same time. It is being stopped at this moment. So whatever the training we have provided to the generator, generator will keep on generating the samples, and will keep on giving the samples from both sides, from the real and the fake one, and discriminator will classify, calculate the loss, reiterate, calculate the loss, reiterate, and so on. So this is the way basically discriminator is being trained. Now coming to the training of generator, here we can see that we have logged the discriminator. We have logged the discriminator. What we are doing, we are locking the discriminator and training the generator. So what locking the discriminator means, we are not training the discriminator at this time. We are not training the this d at this time. Not training d at this time means we have assumed that d is trained enough. Now generator will give a sample. Discriminator will say real or fake. Again, we will get some loss. We'll keep on again training. Again, we'll get some loss. We'll keep on training. And we will get, when we will get the loss, when the discriminator for the generator, if discriminator is giving 1 for the real and 0 for the fake, that means discriminator is doing to is able to discriminate quite well. We, what we have to do, we have to just reiterate. Success of discriminator is basically the failure of the generator and vice versa. Success of one is the failure of other. But it is the success of overall GAN model to have a very trained discriminator and to have very trained generator. Got it. Now coming to the insights of training the discriminator model, that how basically this particular discriminator is being changed. Now look, for example, this is the discriminator model and this is the generator model. What happens? For example, this is the random noise. What is this? This is the random noise. Random noise. What I have already told you, the task of the generator G is to convert this random noise into some other probability distribution. So, for example, by 10th epoch, after 10 epochs, this G has converted this probability distribution Z into this format. And what is the real probability distribution? That is capital D. This is circular form. This is circle. So this is just for the visualization that original probability distribution is like this and the noise is like this. They are totally different. They are totally different at the initial phase. Got it? So for example, after the 10th epoch, this generator is able to change this complete oval shape to this format, which is somewhat similar to the circle. Not exactly, somewhat. And now it is going to give input to the discriminator. Thus, yeah, discriminator take some samples, and discriminator is going to take some input sample from here and input sample from here. So after the 10 epochs, at this particular moment of time, it is quite easy for the discriminator D to discriminate between the real and the fake. Why it is so? Because the shape of probability distribution of this one D dash is very much different from the D. Now that means generator has to try hard. Generator has to try hard. Again, what it is going to do? It is again, it will retrain itself. And after 100 epochs, you can say 100 epoch training of G, it has converted itself from this to this shape. Got the point? Now it will again give some input samples to D. Now it is little bit difficult. It is little bit difficult. Difficult for whom? Difficult for the discriminator, because it has taken some shape close to circle. Close to circle means close to the real one. But again, somewhat we can say that discriminator is able to just classify between the real and the fake one correctly. Again, we are going to calculate the loss. Again, for example, after 10,000 epochs, Z is able to just change this shape from here to here. Now it is even more close to the circle, more close to real distribution D. Now again, it is going to give some samples to this network that is called D. Now this network D is going to take some input samples from here, and from here it is a little bit more difficult for these discriminator to discriminate, because this is a quite good challenge that has been given by the generator. Now after 5000 epochs, this generator G is able to make a shape which is very close to D. That is original probability distribution. That is original probability distribution. Now this is very much close to this one. Got the point? Now it is very much difficult for the discriminator D to differentiate between the real and the fake one. And at this moment of point, we are assuming that it is quite good challenge for the discriminator to discriminate between the generator and discriminator that has been given by the generator. Now we can say that the training of network that is called G is complete, and it is very difficult for the discriminator to discriminate between two of the jobs. That is called this and this one. I hope you are getting this. And if you have any kind of doubt or if any kind of queries coming to your mind, you can just ask. Okay, coming ahead. So again, if I talk about the last function, coming to the point that, for example, this is the data distribution. This is the data distribution, and we can say that this is the px of data. Probability px of data means probability distribution of the real data. And what is the role of the discriminator? Role of the discriminator is to take this probability distribution of the generated data and the real data and to have some kind of discrimination. So when we are going to just feed all the samples or all the dots, each dot represents one data sample. Each dot represent one data sample. So when we are going to just fed all the dots to D, that is discriminator network, then we can say that D is trained, and now this D is trained on data sample X, and it is parameterized theta. What is theta? Theta is, we can say that it is a set of parameters. So we can say that discriminator network D is parameterized by this theta. That is a trained neural network having updated weights and biases. So if I say that what is the trained network means that based on the input samples, that particular network has just updated its weights and biases, and now it is a parameterized network trained enough so that you can just perform future classification kind of things. So if I say that this is the probability distribution Z and this is the generator network G, so what generator network has to do? It has to just take the input samples from the noise and train itself, and based on the that, it is going to generate PZ of X. So what was P data of X? That means it was the probability distribution of the data, and this is basically not the real data. Rather, it is basically generated data, or you can say that it is the probability distribution that has been given by the generator network. And target is quite clear. What is the target? Target is that we have to just make this generated data probability distribution which is very very equivalent or close to the actual. So generated and actual data probability distribution should be very very close. This is basically the target of the discriminator. Now coming to the loss function, so I think it's a little bit mathematical part. So before going to the or before just starting the loss function, we should take a break of. Acha, okay. I was not able to see the uh, basically queries because I have just started. Okay, so before taking the break, I'm looking for the queries because I was not able to see the queries.
Sir, the queries are below, sir, not below chat.
Queries are below.
Yes, sir.
Just check.
These are like other session queries. Yeah,
Acha,
this
these are the
question.
queries from the other sessions. Okay. So do we have any queries in this session?
Yes, sir. This in front of you, the query. That query is yours.
Okay. Just check me. Just see me.
Pradeep, then Aditi,
Okay,
then
so
Pooja.
Pradeep has asked that why this some new messages coming in. Just a minute. Okay, so Pradeep has asked that I have three questions. One is what is the authenticity of dataset generated using GAN? Does accuracy not questionables? How one can compare with state of the art? Okay, so no doubt the data which is being generated by the GAN, if so authenticity of the data depends upon the purpose. So for example, if you are using the data GAN generated data for upsampling, for class upsampling, so might be possible you are asking for the same, that if you want to upsample your data and we have generated data using the GAN based models, then what should be the authenticity? So for checking the authenticity of the generated data, we have some matrices like FID scores and other kind of matrices are available, which are used to check the similarity index of the real image and the generated image. So if the similarity index in the image generated by the GAN based models and the real data is within the threshold that we require, then we can say that this one the authentic one for me. So it depends application to application, that how much close image I actually want. So there are a lot of matrices that you can use in order to check the authenticity and the performance of the particular GAN model. And moreover, if I talk about the comparison, so the answer is same. There are some scores like FID and other kind of similar scores which checks the similarity between the probability distribution of the images in the real as well as generated images, that you can just compare for checking uh, the performance of the GAN models. Second question, you said same distribution. It means it finds distribution type of every image first, then generate same kind of distribution images. Is it so? So same distribution doesn't means we are trying to mimic the distribution of a single image. So, for example, I have a corpus of 2000 or 3000 or 4000 images. So, the model is trained on those images, and if we'll calculate the loss, I will just show you in the upcoming slide that how to calculate the loss. So, the loss is not calculated based on one data sample, rather, it is a cumulative loss of all the data samples. So, it is not basically we are trying to mimic the probability distribution of one sample. We have to just mimic the cumulative distribution of the entire data set, and loss is also compared by having the cumulative sum. because we don't need to generate the images which are similar to a single images. We may have some different kind of images in one corpus of training data, and we have to generate different kind of images. And if our model is able to generate the images of single type and it is not able to generate diverse images, then that problem is also called as smart collapse problem. I will also discuss in the upcoming slide that what is the smart collapse problem and how we can get rid of this. The third question is, can we connect diffusion model and GAN model anyway? No doubt the concept of basically the diffusion model and the GAN models are a little bit different. Why it is so? Because the diffusion model, GAN models start with the random noise, whereas the diffusion model starts with the original image and keep on adding the noise over the course of iterations, and corrupt the original image, make it full noisy image, and in the reverse process, those diffusion particular diffusion models tries to basically remove the noise step by step, by predicting the previous phase, and tries to just get the original image. And no doubt, uh, we are not actually removing the noise that we have added, rather we are predicting the noise that we have added and then removing it. So we are not removing the actual amount, rather we are removing the predicted amount. So the final image that we will get will not be exactly the same as that of original, but it will be very close to that one. So if we want to have some hybrid kind of concept, yes, we can. What you can do, rather than taking some pure random noise in the GAN model, you can just have some kind of corrupted images by some layers of the diffusion model, and then you can just provide to your GAN, and then GAN can do the task for you. So the ball is in your court. You can just get into the architectural details of both one, and you can just uh, uh, have some kind of hit and trials, and just check that you can, if you can get the desired output that you want. Okay, so is there any other query that have been asked in this particular session? I think Aditi. So, okay,
Yes, sir,
Aditi
Aditi
has
has.
asked that I am training the GAN model for image generation task. Then whose loss should be minimum, generator or discriminator, at the end of the training? Because it is like a min max game, both compete with each other. What can be the highest loss difference? Okay, that's really a very good question. And no doubt, it's a little bit confusing one, because what we say that it's a kind of competing approach. Generator tries to fool the discriminator, whereas discriminator tries that we should not be get fooled by the generator. Then who should win? Because it is a min max problem. Why it is so? Because for example, I just want to give an example. For example, I want to make a good cricket team. So I have the bowlers and I have the batsmen. Bowler, in the training process, for example, I have a team and I'm the coach of the team. During the training process, my bowlers are going to bowl for the batsman. So what bowlers will try to do? Bowlers will try to out the batsman. He will try to just bowl him. And what batsman will try to? Batsman will try to just defend him, just have some kind of force or sixes. Now, what the question is that, as a coach, I will just train the bowler first. That you have to bowl the batsman. And when the bowler is able to bowl the batsman, then I will come to batsman. I will try to train the batsman. Yeah, you have to hit the six on him. So I am going to train the batsman even more. Then when the batsman will be able to hit the sixes, hit the boundaries, then I will again go to the bowlers, train them. So my win is to train the bowlers as well as batsmen in such a way that as a overall team we will be able to compete in the international tournaments. Not exactly same, rather you can think like of that as a if you want to have a very good GAN model, you have to train both in a better way as much as possible. So no doubt after some time there will be some kind of convergence, because there is a limit of each and everything. So you have to train the generator, you have to train the discriminator, again generator, again discriminator. Both must be robust enough, so that they can generate good quality of images. uh, for example, if discriminator is not good, then your generator cannot be good, because the things are interrelated. Why it is so? Why I'm saying, like, if generator is not good, then if discriminator is not good, then generator can never be good. Why it is so? Whatever the generator will generate, discriminator will not be able to classify, because it is not good. Then generator will think that, yes, I am skilled enough, I am trained enough, I will not try to, and generator will not try to improve itself. So it will stop the training, and he will think that, yeah, convergence is achieved. Whereas in the vice versa, if my generator is not good, then what discriminator will think? Generator will not able to generate good images. Discriminator will be easy. It will be easy for the discriminator to discriminate both, between the real and the generated images of the GAN, of the generator. So generator will stop the further training, and he will think that, yeah, I should not go ahead, and ultimately your model will not be good enough. So the thing is, we have to just train the generator and the discriminator in an efficient way. Both should be robust enough for getting good performance. Yeah, you already told. Yeah, both generator and discriminator architecture should be strong enough. Any other query before the break? Okay, so let's have a break of 10 minutes. It's 7:30. We can have a break of 9 minutes. I will just resume at 7:40.
Okay, sir.